My name is Joseph Lusoma. I'm here to present a data visualization Paraview assignment. So we are looking at this project where we are looking at the impact of pressure and temperature on this given cylinder. As we can see that the cylinder we have selected, when we select to look at the pressure, definitely when you look at the from the midsection of the cylinder to the bottom, you can notice that there is a visibly noticeably higher pressure in the middle, and it's relatively high as you're going down. But at the upper side, there's relatively less pressure, I think mainly due to the open uh, area at the top. We can also look at the temperature and see the temperature distribution. It's showing basically the temperatures are high at the base of the cylinder. So this is a full cylinder. We went ahead and sliced the cylinder to look at the details of the pressure and temperature distribution in this cylinder. So let's look. So what we are looking at in the sliced version of the cylinder, we are again seeing that the pressure is high, starting from the midsection, and it's relatively high as you're sloping down, but it reduces as you're going to the bottom. We can also look at the temperature. You can see the temperature are high at the base of the cylinder, which is in the middle, and the temperatures are very high in that region, and they kind of spread a bit in the next nearing regions, but the rest of the regions are cold. Um, Again, we wanted to also look at the pressure, the impact of the pressure on the sliced cylinder. So we managed to use a glyph which shows the impact or the direction of the pressure. So you can see that this sliced cylinder shows that the direction of the pressure is towards the external or the frontal end of the sliced part of the cylinder. We managed to come up with a visualization, and the visualization is mostly to show the relative distribution of temperature and distribution of pressure uh, in the cylinder. So this dashboard shows us one. Let's look at the temperature. Let's look at the temperature. Now this cylinder shows us um, a distribution of higher temperature. Now you can notice that at depth 4,500 depth, there is a higher temperature, but as you come closer to the open side of the cylinder, as you come closer to the open side of the cylinder, the temperature reduces. So this is what it's showing. Now from the inner depth, as we are coming out of the cylinder, the temperature is reducing. Now this graph is showing, histogram is showing the two versions. We have a full cylinder version and a sliced version. Now we wanted to show this because temperature distribution in a full cylinder is quite different from the one that is sliced. That's why you can see that the representations here is a full cylinder has higher uh, depth as compared to the sliced one. You can notice that the sliced cylinder give a half of the values as compared to the full cylinder. Now, another thing we want to look at is the pressure distribution. Now, pressure distribution indicates that as as um, as the pressure increases, also the depth increases. So you cannot notice that as we increase the depth, also the pressure increases. However, there are so many factors that contribute to a pressure being high. First of all, you can notice that some areas here have less pressure, other areas have higher pressure. Now, some of these are because temperature is part of the reasons why pressure increases. So, in regions where there is higher temperature, you'll find that we have high pressure. So, that's why in these regions where we are having high temperatures, we are having relatively high pressure distribution in this area. Uh, the final part we want to show is the relationship between the pressure and the temperature. So we notice from here that as temperature increases, also pressure increases. However, when temperature falls drastically or dramatically, pressure also falls, but at a much lower rate as compared to the temperature. So finally, let's look at our current data set. So in this data set, we are going to look at the EQS. So simply the EQS looks at the the measure of the deformation or strain experienced by a material during plastic deformation. Again, we are going to also look at the velocity and EQS, and we are going to see how we can visualize the deformation of the object in blue as in comparison to the velocity. So let's start with looking at EQS. So simply at EQS, we are looking at the level of deformation. Now you can see as time series move on, the level of deformation increases. So deformation increases with time. However, when we look at the velocity, so let's try to play around. So when you look at the velocity, actually you can notice that some areas are much quicker to get deformed as compared to other areas. I think this is mainly because of the level of pressure that it exerted. But there are so many reasons that can happen. It can mean that one side has a less tensile strength, relatively weaker than the other side, or maybe this object has is heavier on one side as compared to others. But according to this flow time series, it shows you that the velocities are relatively higher in some regions and lower in some regions. So the distribution is not uniform across the object. Let's look at um, again the velocity. We went ahead and selected some few points on the image, and let's look at how. So you notice on this given point selected here, you can notice that the velocity was high and low. However, they were not on the same rate, but in terms of movement, the velocity was relatively closer to one another on those given points that were selected. So let's also look at the average EQS of all the components we are looking at here. So we can see that as time moves on, the level of deformity of the entire object also increases. So we can see relatively in the middle, the deformation was relatively uniform, but towards the end, uh, there was a spike in the deformation because all the top elements were joining the elements at the bottom to form a nearly flat surface. Now, finally, let's look at our dashboard. So this is our dashboard that is reading this data in real time. So we can look at EQPS. So you can notice that the surface area of the first points, its deformity increases with time, whereas the regions at the end, their deformity is not much because by the time the load reaches at the bottom, their deformity is not as much as compared to the first regions of the cylinder. So the first region got high, were deformed much higher as compared to the lowest regions. So the average EQPS we can see for the entire block, we can see is that as time moves on, the EQPS increases with time. So as time moved on, the object got deformed. When we look at the velocity, we notice that velocity was relatively different, and it was relative to different regions due to the factors we had talked about. It can be because certain regions are weaker, how are the pressure points of the pushing object might be not be uniform. So these are some of the reasons why the regions are not deforming at the same rate, and it's why the velocity is a bit different. Once again, my name is Joseph Lusoma. Thank you. And that was my presentation.